Thermodynamics has a reputation as being difficult. So I'm just going to go through and talk about the main points and some things that probably need some explaining. So imagine a cylinder of gas with a piston in it that we can use to contract or expand that gas. That gas will be our system. Now be intimately familiar with this because we're going to be thinking a lot about the system of gas. So now imagine there's a little man in that cylinder and he's pushing the piston up and the gas is expanding. Is he not doing work? He's providing a force, the piston is moving a distance. So yes, he must be doing work. Work is the transfer of energy. So there must be energy transferred from our system of gas to the surrounding air. So you're used to thinking of work as force times distance. But now that we're looking at systems of gases that might have very irregular shapes, this isn't the equation to look at anymore. What we should look at is the change in volume of a system and the pressure of the system. The work done by a system of gas is its pressure. Hopefully it's a constant pressure. Then we can use it in this equation. Times the change of volume that system undergoes. And then, okay, what is Q? That's the heat transfer we've just seen in the previous chapter. So that's energy that flows from, into or out of the system because its temperature is different than the surroundings. But for the work we're looking at, it isn't necessary to have a temperature difference. In fact, work could transfer energy from a colder system and make it even colder than it was before. So this first law of thermodynamics is basically saying, look, there's two ways for the total internal energy of a system to change. One is from normal heat transfer, due to temperature difference. The other is from work, which is due to the change in volume of the system. And by the way, if the volume decreases, then work is done on the system and the system gains energy. Another thing that you'll become intimately familiar with is a pressure-volume diagram, where we have pressure on the y-axis and volume on the x-axis. Now there's 4 types of changes you should understand. We can figure out what they are based on their names. So if you know iso means same, it helps. And what about barometer? Barometer measures pressure. So isobaric means that there's going to be the same pressure throughout this process. Isochoric is just another word for isovolumetric, so yeah, that means the volume doesn't change. And isothermal means the temperature doesn't change. We think of therm as meaning heat, but the one about heat is the adiabatic. So adiabatic is where there's no exchange of heat. That doesn't mean no energy can go in or out of the system. It just means that there's no heat exchange due to a difference of temperature. So it might be the system might be at the same temperature as the surroundings for the whole time, or it might just be really well insulated, like in a vacuum. Okay, now let's match these 4 processes. So which of these 4 lines looks like it's isobaric? We would have to have the same pressure at all points. And it looks like this is one here, this horizontal left to right line, where the pressure is stuck at this value here, whatever it might be. So there we go. That one's isobaric. It could go left, it could go right. And isovolumetric, the same volume. We got to be stuck at one volume. So this is a process that's either going straight up or straight down, and we have found it here. And then the tricky one is distinguishing isothermal from adiabatic. But before we do that, let me point out another interesting thing. For an isovolumetric process, if delta V is always 0, and that's the definition of an isovolumetric process, then there's no work done. So in an isovolumetric process, all of the change of internal energy is due to heat Q, and in an adiabatic process, all of the change in internal energy is due to the work. Okay, now back to the hard part, distinguishing isothermal from adiabatic. So let's imagine a process where we're squeezing down our gas, we're pushing in a piston, contracting the gas. Maybe we're doing this really quickly. So what must happen to this sample of gas? It must receive energy because work is being done on it. Its volume is contracting, the outside atmosphere is pushing with a force over a distance, and if it's gaining energy, its temperature must be increasing. Why? What is temperature but a measure of the average kinetic energy of the gas molecules? Now, if we have the same number of gas molecules and they have more energy now, there's more internal energy, the average energy must be higher. So the temperature went up, and if this, let's say this happened really quick, or in a vacuum or somewhere very well insulated, such that maybe there wasn't time or the ability to lose any of that that heat to the colder environment. So at least for the beginning part of this process, it's adiabatic. But over time, if it's not well insulated, it's going to lose heat energy since it's hotter than the surrounding. And if it goes back to its original temperature T1, now we can call it an isothermal process. But what happened during that time that it cooled off? What happened to the pressure in here? Hopefully you should be able to tell me how the pressure changes if the temperature cools off. It would be a decrease in pressure going from here to here, right? So as we go from adiabatic to isothermal, our pressure decreases. So here's that, the pressure decreasing at the end of our process of contraction. A quick way to distinguish an isothermal curve from an adiabatic curve is that the adiabatic one is going to be steeper, which is the case in both over here in this slide and in our example. Just a little note here, a clarification. When I talk about very quickly compressing the cylinder and doing an adiabatic process and then letting it cool, we end up where we would in an isothermal process, but it wouldn't be the same as the isothermal process when it was cooling the entire time. So the true isothermal process might be slower, where the temperature stays the same during the entire process. My way to compare an adiabatic versus a isothermal process is to say, hey, look, let's do an adiabatic process and then see what happens to the pressure as it cools off after the contraction. So yeah, my theoretical hypothetical process would look like this. And you'd end up at the same place as if you'd done an isothermal process, but the process itself wouldn't be isothermal. Okay. All right, now I'm going to jump ahead and talk about engines. It's important to remember the equation for work when we think about this. In fact, every time this piston goes to the right, we can think of the engine as doing positive work to move the train or the whatever. Every time the piston goes back, we can think of it as doing negative work. So the key to having an engine work is to have it do more work when it goes this way than when it goes back that way. And since the piston is going the same distance right and left, delta V is the same whether it's expanding or contracting. So what has to be different is the pressure. So in order to make the work greatest done when the piston's going to the right, you want the pressure to be as high as possible during that part of the process, and then you want the pressure to be as low as possible during the reverse part of the process. So the steam, the heat and the steam coming in from the top make the pressure high on the stroke to the right, and then the cool water down here, its role is to reduce the pressure by reducing the temperature, but also by condensing the water vapor in here and reducing the amount of gas in there. And therefore, a more efficient engine is going to have a higher difference between the hot temperature up here and the cool temperature down here. It's important to understand that a Carnot engine is like an idealized engine. So this isn't exactly how engines work, but it's how they should work if everything goes ideally. So all right, here's what happens in a Carnot engine. The first step is the expansion of the cylinder. This is what the productive work that drives the engine to move the car, or the train, or whatever. And this is going to be an isothermal step. Remember, that's our flatter one compared to the adiabatic step. The second of the 4 steps is a continuation of the expansion and continuing to drive the motion of the car or the train. But this is an adiabatic step, so I'm drawing an adiabat here. So during that second step, there was no heat exchange, so you'd want to somehow insulate the cylinder during that process. And now we get to the point where the piston changes direction and starts to contract again. And it's important how it goes back. We want to do as little negative work going back as possible. Now, if we went back in 2 steps adiabatically and isothermally, we'd follow the same lines, and we'd erase all the work we just did. So we want to start our retreat backwards as flatly as possible. So that would be an isothermal line. And finally, our last step is an adiabat again, the steep one. So how much net work did we achieve in this one cycle? It's important to know that the work done in a process is the area under the pressure versus volume curve. So for the first step, the area under the first isotherm and the first adiabat is everything in here. So if we didn't have to go backwards with our piston, this would be, this area would be the amount of work done. But we do have to go backwards, so we have to subtract out all the area under the retreating isotherm and adiabatic lines. So if we take our first positive area in black, subtract the area in red, what we end up with is the area inside the curve. And a lot of times you can you'll get an area that looks like a triangle or a square, and you can just say, okay, the area is close to the area of this triangle, and do half times one side times the other side length. Now, engines work because they take advantage of a temperature difference and the fact that heat will want to flow from something at high temperature to something at low temperature. But for a air conditioning unit or a heat pump, we change the direction. We put in a little work, maybe through an electric motor, to help us move energy from the cold side to the hot side. Does it look like you're actually ending up with more heat going into the hot side than you put in with work? Yes, that actually happens. With an air conditioning unit, you move more energy than you buy. So the energy, that's coming out of your electrical socket to work your air conditioning unit is less than the total amount of energy you're pulling from your room. Or I guess a better example would be a heat pump. If you turn around your AC unit and this is the outside and this is the inside of your house, you're paying for less energy than you're getting into your house, because you're getting all that energy from the work plus some energy that went from the cold outside to the warm inside. A lot of people have a big issue with this because they think that it violates the law of the conservation of energy. You can't be more than 100% efficient, but actually you can be more than 100% efficient, and it's because you're not creating more energy. You're just moving energy from one place to another. Even though it's cold outside, it's not absolute zero outside. So there is still internal energy in the system of air outside. Okay, here's a representation of a heat pump. And let me reiterate, it is possible for you to pay for 1 joule of energy from the electric company and move 3 joules of heat inside your house. Let's verify again that doesn't break any of the laws of thermodynamics. So the first law is that we can say energy is conserved, or change in internal energy is heat plus work. Well, here's your Q movement, here's your W movement, your work, and that equals the change of internal energy inside the house. So we follow the first law, and then the second law of thermodynamics says that the entropy of the universe increases over time. Well, it's hard to tell just by looking at this diagram, but another way to state the second law is that energy will spontaneously flow from a hot thing to a cold thing, which is not happening here, but also this is not a spontaneous movement. We're putting in a lot of work to make heat flow backwards. So it's a non-spontaneous movement of heat backwards. So a heat pump doesn't break any law of thermodynamics when it's more than 100% efficient. It might have a coefficient of performance of maybe 3, but a propane heater, kerosene heater, a plug-in electric heater, none of these could go above 100% efficiency. And therefore no other type of heater could have a coefficient of performance greater than 1. Now let's take a closer look at how AC units, heat pumps, refrigerators actually move heat from a cold to a warm place. So let's start by looking at the motor of the refrigerator here. So it does work to compress a refrigerant fluid in here. It might come in as a gas, but then it gets compressed under higher pressure and it becomes a liquid. And we know that condensing is a process where heat is released. So these coils get hot. When I was a kid, I used to, in the winter, I would lay down next to our refrigerator because hot air from the condenser coils would come out from under the bottom of it. So this is how more heat is added to the hot side. The hot side here is your kitchen. Alright, but then this is where the magic happens in the cooling coils. So these are inside the refrigerator. They actually get cold and cool off the inside of your fridge, make the cool side even cooler. And here's how they do it. First, think of the work that's being done. Um, they are doing positive work and therefore losing energy, since the high pressure in here is released and gas expands through these coils. The gas in there is expanding a positive delta V, and work is being done by the gas in these coils. Therefore, uh, they are losing energy from work, and that's cooling them off. And if you're at home and you want to see this process work in real life, just grab one of those uh, air sprayers that's supposed to clean off your keyboard. It's just a can of air. If you spray that thing for a few seconds, you can feel it get cold, because the same thing is happening there. Gas is expanding as it comes out, doing work and losing energy, and therefore the temperature is lowering. But here's the kicker. Um, you also have evaporation going on, since you have a liquid here and it's evaporating to be a vapor in the cooling coils. So we know that that process of evaporation requires energy. Uh, so so that's going to pull energy from your refrigerator, which cools it off. And back to the keyboard duster, the air in a can. If you really want it to get cold, don't try this at home, because you might actually get frostbite. But if you turn it upside down such that it forces the liquid in the can to come out, it's going to evaporate and expand, and it's going to make it really cold. And you can actually freeze water. Like if you pour water on the table and blast the upside down air can onto that water, it will actually freeze.